Hello, my name is Victoria Grimes, and this is my Physics 2 Lab 1 where we're doing charged tapes. Let's get into it. The purpose of this lab was to utilize household objects such as tape to demonstrate and observe the transfer of electrons between surfaces, estimate the number of electrons transferred, and determine the respective charge of the tape. The fundamental principles we used were Coulomb's law and Newton's second law. For Coulomb's law, we used tape to model point charges, and we assumed equal and distributed charges across the tape to use this principle. And we used Newton's second law, F equals ma, and we used the approximate dimensions of an atom to calculate the number of deficient or excess electrons per atom on a charged piece of tape. So for our preview of our results, the charged pieces of tape were determined to be positively charged. The charged tape pieces repel each other. The charge on each piece of tape was 1.0501 times 10 to the negative 8 coulombs, and each piece of tape was calculated to be deficient of 6.56 times 10 to the 10 electrons. Now on to our assumptions and models. Each tape piece was used to model a point charge in order to observe electrostatic interactions on a larger scale, and the assumptions we made was that there was no air resistance. The tape pieces represented point charges with charge concentrated at the center of the tape, and each U-tape piece had an equal surface distribution of charge. So for our experimental setup, we have our system and surroundings. System is tape A and tape B, and the surroundings were everything else in my room and outside. The initial conditions were 2 pieces of tape assumed to be neutral and equal in length, and also 2 pieces of neutral tape stuck down onto the desk. And the process was that tape A was stuck to the tape on the desk to create a charge. Tape A was hung around several objects to determine its charge, and then tape B was charged similarly. Tape A was placed above tape B until a portion of tape A floated, and the distance between the 2 tapes was measured to later calculate the charge. Pictured on the right is the setup that I had. It's kind of jank. And pictured on the left is a demonstration of the tape floating. Now on to our observations. So we figured out that the U-tape, tape A, was attracted to my hand. Tape A was also attracted to a neutral pack of cards as seen on my desk. Tape A was also attracted to a negatively charged plastic cap on a pen, and tape A was repelled by tape B, as you could see in the previous slide. And the conclusion was that tape A and tape B were positively charged and lost electrons in the charging process. For our data and calculations, so we have the tape mass, tape length, tape width, and the distance between the tapes. And then we apply Newton's second law, which is F equals ma, which is also equal to mg, and g in this case is 9.81. But we know that the acceleration for the tape is going to be equal to 0, so our forces are balanced. So our electric force and gravitational force are balanced. And with this information, we were able to calculate what the charge on a piece of tape was. Furthermore, we were able to calculate the number of electrons lost by a piece of tape by dividing the charge of the tape we just found by the charge of an electron, which is 1.6 times 10 to the negative 19 coulombs, and we got 6.56 times 10 to the 10 electrons. We also found the area of a tape, the area of an atom, and so the number of atoms on the tape were going to be the area of the tape divided by the area of an atom, and we got the ratio of electrons to atoms by just dividing the two. Presented here is my glow script code where I input the values such as the mass, the tape length, tape width, the distance between the tapes into the code, and we were able to output what you'll see in the next slide. So on to results and discussion. So as you can see on the right, the charge on one piece of tape was 1.05 times 10 to the negative 8 coulombs. The deficiency of atoms on one piece of tape was 6.56 times 10 to the 10 electrons, and there are 6.18587 times 10 to the 6 atoms for every electron on one piece of tape. And so there are some model discrepancies because this is not a real point charge, and the charges on each tape truly have unequal charges. And we have some sources of experimental errors such as charge transfer when I was handling the tape. It's been very humid recently, and also that there are unequal charges on each tape, meaning that the Q was likely not the same for each piece. Finally, there are some conclusions that we can draw that everyday objects can be used to observe electric forces at play on the nanoscale. Common objects can be easily charged through touch alone, and that electric forces and fields are important information and play a large role in how we interact with the world around us. Thank you.